Okay, let's get a few more theorems about convergence of series. And I want to do a little bit of a lemma first. And the lemma says that, well, the convergence of a sequence or a series really only depends on the entire tail of the series. The first terms don't really matter, right? I kind of only worry about what happens when n gets big. So I can cut off the first billion terms of a series, and if the tail still converges, the entire thing still converged, because a billion times a finite number is still a finite number, plus whatever the convergence at the end was. So let's just write down a little lemma. So a series say sum from n equals 1 to infinity a sub n converges if and only if for each k the sum from n equals k to infinity a sub n converges. Okay, I'm going to leave that as an exercise to you, but what this means is I can cut off however many terms I want to at the beginning and just look at convergence after some point, and then the whole thing converges if the tail converges. Right? A series converges if and only if the tail converges. Okay. And sort of the hint is, well, if I've got a finite number of terms, there's a maximum there, and so taking a finite number times a maximum is still finite. I can add that to whatever I get from the tail, and that would give me the entire series convergence. So the beginning doesn't really matter because it's finite, and in convergence all I'm worried about is what happens near infinity. Okay, so let's look at Kosice's criterion here. This is a criterion about when sequences converge or not, and the power of it is going to be that I don't actually have to know what the limit will be to prove convergence. Definition of convergence says that a sequence converges to a limit if the difference between that limit and the entries in the sequence gets small. Well, to use the definition of convergence, I kind of have to know what that limit is so that I can subtract it from the terms in the sequence and take the absolute value. Kosice's criterion avoids that trouble of having to find an actual limit to compare things to. So let's go with this. So a definition: a sequence S sub n equals 1 to infinity is said to be Cauchy if for each epsilon bigger than 0 there is an n, capital N, in the natural numbers such that if n and m are bigger than n, then the distance between S sub n and S sub m is less than epsilon. Okay, so this just says that all of the entries in the sequence eventually get really close to each other, right? No matter which n and m I pick, they're within epsilon of each other if I'm far enough out in the sequence. Okay, the theorem, Cauchy's criterion, then, this theorem this is for convergence. a real valued sequence say S sub n converges if and only if it is Cauchy. Okay. So if I can show it's Cauchy, if I can show all of the terms in the sequence get close together, I don't actually have to find a limit to prove that a limit exists. Okay, that's going to help us out a lot for series, because actually computing what something adds up to is pretty difficult. So we're going to avoid that trouble when we're proving things, because I don't have to figure out, okay, what does this sum actually equal? I can just say, well, all of the terms get close together, or all of the partial sums get close together, so that there has to be a limit somewhere. I can just say things about convergence that way. All right. I'm not going to prove this. The book proves it, but it is pretty technical. I'll have you guys read it. It is 3.8 through 3.11. 3.11 is what this Cauchy criterion theorem is. This is 3.11 in the text. But it does get kind of technical. And at 3.12 talks about other spaces that the Cauchy criterion holds. It doesn't just have to be real valued sequences. Other things work for where all I have to do is show that the sequence gets close together, and we'll use that if we get to convergence of sequences of functions at some point in time, maybe in week 4. But for now, we're gonna go with the criterion for real valued sequences, because we're going to be working with series, and series are real valued. Okay, so let's see the first instance where we're going to use this Cauchy criterion, and that's the comparison test. So let's write down the comparison test. It kind of comes in 2 parts. So the first part is if the absolute value of A sub n is less than or equal to C sub n. So A sub n is a sequence and C sub n is a sequence. Eventually. So what do I mean by eventually? For all n bigger than n naught for some specified n naught and n, sort of eventually, or in the tail of the sequence. Right, I just talked about the beginning of the sequence doesn't really matter, it's just the tail that matters. So if I go far enough out, I have that the terms of A sub n are smaller than the terms of C sub n. Then, if sum of C sub n converges, so does the sum for A sub n. I'm going to leave off the subscripts from n equals 1 to infinity or k to infinity. They don't really matter as long as you kind of think about infinity. Where I start doesn't really matter. We had just mentioned that with the tail. So the book kind of leaves off the subscript and the superscript for n equals 1 to infinity. I will here too, because where we start these sequences doesn't really matter for convergence. The second part to this is, so the first part says if I add up smaller things, I also get to be a finite sum. the second part says if I add up bigger things and it diverged, then the bigger sum also diverged. So if a sub n is bigger than or equal to d sub n is bigger than or equal to 0, eventually, in the tail, then if the sum of d sub n diverges, so does the sum of a sub n. Okay. So first part says that if I add up smaller things and the bigger things converged, the smaller things also converge. Second part says if I add up bigger things and the smaller things diverged, so do the big things. Kind of makes sense, right? Adding bigger things together would just be bigger than whatever you got in the first place, and or adding smaller things together would just be smaller than whatever you got in the first place. So let's prove part one. Part one's where we're going to use the Koshice criterion. So let's look at the sum of a sub n from n equals m to, let's go with k's so that it looks a lot more like Koshice criterion. So k equals n to m. So if I want to show that as small, I can use the triangle inequality repeatedly to show that that's smaller than that. So that's just the triangle inequality on each of the terms, and by assumption that's smaller than or equal to the sum from k equals n to m of c sub k. Alright. This is where we're going to use Koshice criterion now. So by Koshice criterion, there is an n such that the sum c sub k equals n to m in absolute value is less than epsilon. So Koshice criterion says look at two partial sums, take their difference. Well, this is the partial sum up to m, the nth partial sum minus the nth partial sum, and there will be some point where that's less than epsilon. Using this same n, then we get the Koshice criterion on the sum k equals n to m of a sub k, i.e. a sub k converges by the Koshice criterion. Okay, so that's the first comparison. The second one is easier. I don't have to use the Koshice criterion. So if the sum of d sub n diverges, because each of the d sub n's was non-negative, it's the partial sums form a monotonically increasing sequence. A monotonically increasing sequence, and because it diverges, this monotonically increasing sequence must be unbounded. So the partial sums of a sub n are also unbounded. So they're also an unbounded monotonically increasing sequence. And diverge too. Okay, so that proves our comparison test. Okay. So let's see some examples. Okay, so how do I actually calculate the sum of a series? There are basically just two ways to do it, and one of these is a special case of a way that we'll see earlier, but the first one is geometric. The geometric series is a special case of another way to show convergence, and so I'm just going to go with the geometric one now. We don't have quite the tools to show how you do it. Otherwise, the other way is telescoping. So we'll see a geometric series and we'll see a telescoping series, prove convergence in those two series. These aren't the only ways to prove convergence. They're about the only ways that we can actually find what value a series converges to. So, geometric series. So I'm going to add up 1/2 to the n from n equals 1 to infinity. And we want to figure out what this is. So this is something that you might show your kids in an elementary algebra class. And one of the jokes in the in Kosice's cantina talks about getting half of a glass full, and then a quarter of a glass full, and then an eighth, and then the bartender just pours one glass. Well, why is that? Well, let's look at the partial sums of this series. So S sub k is going to be the kth partial sum. So that's going to be 1/2 plus 1/4 plus 1/8 plus ... plus 1/2 to the k. Alright, each one of these terms is half as big as the next one, so I'm also going to write down 1/2 of S sub k, and that's going to be 1/4 plus 1/8 plus ... plus 1/2 to the k plus 1/2 to the k plus 1. Okay, if I do that, I can pair up all of these terms in the middle, and if I subtract this, I can cancel off all of these terms. So what happens is that cancels with that, that cancels with that, the middle guys cancel with the middle guys, this guy cancels with this, and I'm left with, on the left, I'm left with S sub k times 1 minus 1/2 using the distributive law, and on the right I'm left with 1/2 minus 1/2 to the k plus 1. So instead of having to write out all those terms, I can figure out what the partial sum is. The partial sum is equal to 1/2 minus 1/2 to the k plus 1 divided by 1/2, or 1 minus 1/2 to the k. This allows us to now compute the limit of the S sub k's fairly easily. So the sum from n equals 1 to infinity of 1/2 to the n is equal to the limit as k goes to infinity of S sub k equal to the limit as k goes to infinity of 1 minus 1/2 to the k equals 1 because this guy heads off to 0. So the joke about the bartender pouring just one beer is because the first guy just gets to drink half of it, the next guy drinks half of what's left, and I wouldn't want to be like the fifth guy, but that's what the joke is. Okay, so let's see how this works in general for a geometric series. So a geometric series has a constant times a ratio to some power. Usually we'll start at n equals 0 and go off to infinity. So a is the first term of the series, and each term to get to the next one you multiply by r. So this is equal to a over 1 minus r. And let's prove this. If the absolute value of r is less than 1. So proof. S sub k is equal to a plus a times r plus ar squared plus dot 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 plus ar to the k. R times s sub k is equal to a times r plus ar squared plus dot 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 plus ar to the k plus ar to the k plus 1. If I subtract these, what we end up with is 1 minus r times s sub k is equal to a minus a times r to the k plus 1. So s sub k is equal to a times 1 minus r to the k plus 1 over 1 minus r, and the limit of the s sub k's, which would give me the sum of the entire series as k goes to infinity, is equal to a over 1 minus r as r to the k plus 1 goes to 0 when absolute value of r is less than 1. So that's how you prove that the geometric series converges to what it does. Okay. The other way that a series can converge is telescoping, and what telescoping says is the partial sums, they kind of collapse because you're adding the same thing and then you're subtracting it later, and then you add another term in and you subtract it later. And those middle terms sort of telescope down like an old-timey telescope that like slides out and slides back in, and we can find the limit of that condensed partial sum. So let's see an example. Series. And there's not really a theorem to this. This is just kind of a technique that you get to use on certain types of series. So I'm going to add up the series from n equals 1 to infinity of 2 over n squared plus 2n. So that does not look geometric at all. It's got a rational expression in there, not an exponential expression, so definitely not geometric. It's not arithmetic either. So what am I supposed to do with this? Well, I can use sort of partial fraction decomposition, and we'll take 2 over n squared plus 2n, and we'll rewrite it as something over n plus something else over n. Sorry, I want a minus sign here. No, I want a plus sign, sorry. Over something else time over n plus 2. If I do my arithmetic right and get a common denominator then. I get a times n plus 2 plus b times n over n squared plus 2n should equal this, depending on how I choose the a and the b, or which a and b work for me. Well, to have two fractions equal, their numerators have to be equal, so this would imply that 2 is equal to a times n plus 2 plus b times n, no matter which n values I choose. So let's choose n equals 0, and I get that a equals 1 if I select n equals 0, and if I select n to equal -2, that's going to tell me that b equals -1. So I could rewrite n over n squared plus 2n as 1 over n plus -1 over n plus 2. Okay, that's going to allow me to sort of telescope these partial sums. So the sum from n equals 1 to infinity of 2 over n squared plus 2n is actually equal to the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 2. Okay, this gives me s sub k. It's equal to 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5 plus ... plus, let me add some at the end here, 1 over say k minus 2 minus 1 over k plus 1 over k minus 1 minus 1 over k plus 1 plus the last term in s sub k would be 1 over k minus 1 over k plus 2. Okay, can you see why this is telescoping now? So what telescopes is, I've taken away 1/3 here, and then I've added 1/3 there. And then in the next term, I'll take away 1/4, and the first part of this next guy will be to add 1/4. And the next one, I'll take away 1/5, and then I'll add 1/5. And so those guys cancel out. The last term of a set cancels with the first term of a set 2 sets later. So this first term of this set must have canceled with the last term of a set 2 before it. The first term of this set canceled with the last term of a set 2 before it. The first term of this set cancels with the last term of the set 2 before it. The only terms that don't cancel are these first 2 first terms and these last 2 last terms. Okay, so s sub k is equal to 1 over 1 plus 1 over 1/2 minus 1 over k plus 1 minus 1 over k plus 2. All right. Now I can take the limit as k gets big. Of s sub k is equal to, well, 1/2 plus, 1 over 1. 1 over 1 plus 1 over 2. Because this thing goes to 0 and this thing goes to 0 as k gets large. So this is 3/2, which tells me the sum from n equals 1 to infinity of 2 over n squared plus 2n equals 3/2. And that technique is called telescoping series. So we'll see some more examples, and the geometric example is a special case of computing the sum of a series using a Taylor series. We don't have Taylor's series quite yet. We've got Taylor's theorem, but we'll get to Taylor's series pretty soon.